evening and welcome to Tinkering with Edkiller. For this episode, I have another piece of early 1980s era logic troubleshooting equipment, an HP-5005A signature multimeter. It sports a bit of a weird form factor, especially the permanently attached probes. I have never seen that in modern-ish HP gear before. Any probes or pods are usually plugged in. The last HP device I saw with permanently attached leads or probes were tube devices. The design certainly sticks out. So, what is this thing? The 5005A is the continuation of the Model 5004A signature analyzer. Finally, HP model numbers that make some sense. Okay, let's get serious. This meter is targeted specifically towards troubleshooting mass-produced digital circuits, and the feature set reflects that. The probe tip, which looks like one of the logic probes I showed in a previous video, is the main input device here. Not the typical leads you'd expect on a voltmeter. The probe shows the same visual signals as the logic probe when the digital input mode is selected. Dimly lit up with a tri-state or indeterminate level, off for low, bright for high. However, it does not have the memory function. The pod with the 4 additional wires is used for the more advanced features like the key signature analysis. More on that later. Other digital measurements include a millisecond timer and a pulse counter. As a more traditional multimeter, it features DC voltage measurements, both absolute and relative, as well as a resistance measurement. And that's it. No current or AC with this one. But compared to the aforementioned 5004A model, quite a bit more than just signature analysis. Now, let's look into it. The device arrived in the usual, slightly dirty state, but at least it seems complete. The probe tip is in a sad state though. The sticker is peeling off and needs replacing. The inside reveals a few PCBs, connected with ribbon cables. It has a very similar look and feel to it as the 4951C protocol analyzer. There is a linear power supply right next to a fan. Whoa, I didn't expect a fan in this device, much less right in the middle of it. Strange design. Trying to remove the main PCB. The transformer seems to be holding it down, but that was a red herring. The front panel is held in place with tension springs for some odd reason. I don't want to put too much force on the mounting points yet, so I unhook them first. Eventually, the front panel does come off, but all the wires are soldered in place. The little sandwich of PCBs lifts off on a set of hinges. Now the last screw for the main PCB is accessible. The large screw-on type filter cap seems to be leaking. Removing the probe. The strain relief is screwed on. The pod's case is snapped together. Inside is a very similar design. Screw-on strain relief and soldered wires. On both ends in this case. The pod actually has 3 input signals and a ground connection. Each signal is passed to the instrument via an individual coax line. The smaller PCBs look interesting. Oh, I feel called out. Desoldering the probe leads on the main PCB. The front panel really needs a clean, and these need to come off first. The little grey box on the PCB is a controller for the brushless fan motor. And finally, the front panel assembly comes apart. The buttons also need care. Since I want to avoid dunking the PCB in the sink, I'll just pull them off. Some are easy to pull, others are stuck pretty bad. The switches are the same bent spring type that I already covered in the Microlab video. You can check there for a description on how they work. I tried to clean the PCB with the switches attached. but that proved suboptimal. All the gunk just flows into the contact surfaces inside. I gave in and cut off the heat-staked pins to gain access to the contacts. Cleaning all the dust and residue off is much easier with the switches out, and as you can see, there was quite a bit of stuff to be removed. After gluing the switches in again, it is time for the front panel assembly. It is much easier to put the PCB in first and then add the front panel cover. Whoops! One of the hold-down pins fell apart, but it seems to be holding up good enough even with only 2 of the 4 prongs, so I'm not worried yet. The panel cover goes in next, followed by the hold-down bar on top. Now the buttons. I make sure to support the PCB when pushing them on so that the hold-down pins aren't stressed any further. The buttons could use some retro bright, but at least they are all clean and share the same shade of yellow. I'm okay with that. Resoldering the probe tip wires. And closing the probe. Good. The pod wires are a bit more difficult. The thick PCB with grounding planes makes for quite a bad soldering experience again. I realized, after checking my pictures, that HP has put the color code of the wires on the PCB. G, R, Y and B. Nice. The coax lines are a bit more challenging. These wires are springy. It's just one thin core at the center. The shield in here is even more daunting. The screws go through the wrapped around parts of the shield, the PCB, and then screw into the strain relief on the inside. And all that while not shorting out anything against the shield. But eventually, it fits. Giving the main PCB a good clean before the recapping. Recapping time! I even found a matching screw-on type cap for the leaky one. Another weird cap. This one had 3 pins, 2 ground and 1 positive pin. I ordered the closest match I could find, but the pin out is slightly off. So I had to replace it with a regular 2-pin version. Multi-pin capacitors are for mechanical stability, and the new one is slightly smaller anyhow. And getting things mounted again, starting with the mains switch. The fan is just there for a spacing test, ignore that for now. Now to the mains input block, including the transformer and voltage selection unit. Next, the fan. And before soldering in the probe and pod wires, I did a quick sanity check on them. And I'm glad I did. Turns out that 2 of the pod wires were shorted to ground. Whoops! I thought I might have pinched them in the pod, but no. Could have made good use of the time domain reflectometer here, but that was only almost finished when I had this one on my bench. So I had to find the fault the old-fashioned way. Wiggle and pinch the wire and find out where the short temporarily disappears. After a bit of back and forth, it turns out that the part where the cables are going through the front panel is the location of the fault. Must have been bent too tight for storage. I stripped the insulation and shielding back a bit and found this little dark spot. Looking closer, it's the inner wire poking through. Yikes! That little conductor broke and wiggled its way through the insulation eventually. I'm reasonably sure that this thing hasn't worked properly in ages. Coaxial wire repair is fun! Not. I did my best to reconnect the core, put some heat shrink tube in for isolation, and also soldered the braided shield back together. I did not, however, cover those to keep the result small enough to fit through the original grommet. That way, I only lost a few centimeters worth of cable. After connecting everything back up again, a quick first function check. Seems all the buttons and LEDs are working. Red LEDs. Classy. And the voltmeter needs some calibration. It was only off by a very tiny bit. I think this unit held up quite well. I'm still not sure what benefit the spring-loaded front panel would bring. These are way too tight to allow it to flip open. And with the rubber feet, the case is complete. The accessory lid is next. As the cable issue has shown, careful when putting the pod away. Make sure that there is no sharp kink in the wires. Doing a quick function check. I brought out the microlab for that. DC voltmeter. Check. Differential voltmeter. Check. In this mode, the initial voltage will become 0, so any subsequent measurements show positive or negative offset. Can be useful to find supply rail issues. Peak voltage mode. Check. Either positive or negative peaks can be captured. Delay. Check. The number of milliseconds between a start and a stop signal. Totalizer. Check. The unit can count the number of pulses between a start and a stop signal. Clock frequency. Check. Close enough to the expected 2 MHz. Resistance. Check. The probe tip and ground surface inputs, the example is a 10K pull down. And last but not least, the infamous signature analysis. In this mode, you can hook up the pod to the clock of the device under test. Furthermore, the start-stop signal needs connecting, and then the probe serves as a data bit input. Now what does it do? The device will pull in every bit on every clock between start and stop signals and compute a 16-bit CRC from the data stream. That CRC is then shown with slightly customized symbols to prevent misreading when the display is upside down or at an angle. Of course, these CRC codes only make sense when you have the expected reference values. These would have been provided by a reference list in a repair manual or by a working device for reference. Oh, and the rear features 3 5-volt sockets to connect the logic probes. For the probe, I recreated the sticker in Inkscape. And after printing it on stick-on silver paper, I cut out the strips and voila! Looks like new! Now let's look a bit at the digital part of the circuitry. The voltage levels of the data probe, the clock input and the pair of start-stop pins can be adjusted individually, either to a fixed preset or manually to a voltage of choice. These selected voltages will then be created by 4 individual digital to analog converters and fed into a quad comparator chip to create a digital output. That quad comparator chip is a custom HP one. White porcelain carrier with a golden cap. A beautiful example of when technology was also made to look the part. That tiny sticker looks a bit lost here. Oh well, I also printed them in a larger version. And that's it, a nifty little meter for the digital workbench. The 5004A model signature analyzer that I mentioned in the intro was just that. No multimeter or timing measurements, just the checksum. Now, while the algorithm is an honest-to-God hardware-based CRC, the modulus, or magic number, is different than the usual ones. I hope you enjoyed this episode. See you next time! The front panel really needs to come clean and yes, of course, the front panel needs to come clean. Yes, of course, naturally. What has he done?